So in this video, I'm going to talk about chapter 3.5, the real zeros of polynomial. So when it comes to polynomial, sometimes we will get different zeros, such as complex zero. Real zero means the zero that you can find it on the number 9. So if I'm given a polynomial, fx equals to an x to the n plus an minus 1x n minus 1 plus a2 s2 plus a1 s1 plus a sub 0, and let m be the largest of the coefficient in absolute value. Then all the real zeros of fx lying in the interval negative m over absolute value an minus 1 and m divided by absolute value of the highest coefficient, highest degree coefficient, the leading coefficient, plus 1. So this is called Cauchy bound. It helps you to identify, determine where is the zeros at. 0 means the roots or horizontal intercept. That means when y equals to 0, what do you have? Okay, so let's say if I'm giving you a polynomial, fx equals to 2x fourth plus 4x cubed minus x squared minus 6x minus 3. Determine an interval which contains all the zeros of the function fx. So then we can apply to our Cauchy bound, which is the largest coefficient in absolute value. So the largest coefficient is negative 6. So m is equals to absolute value of negative 6, which is 6. And then an is equals to 2. So that means our Cauchy bound is equals to negative 6 divided by 2 minus 1. And then 6 divided by 2 at 1. So our Cauchy bound is from negative 4 to 4. So all the zeros of the fx function is going to be in the interval from negative 4 to 4. Okay, another theorem is called rational roots theorem. That means given you a polynomial, fx equals to an s to the n plus an minus 1 xn minus 1 here with a integer, with the integer coefficient if r is the rational zero. Then r is of the form r equals to positive or negative p over q, where p is a factor of the constant term and the q is a factor of the leading coefficient. All right, so what does that mean? So let me give you an example. For example, I have a polynomial 2x to the fourth plus 4s cubed minus x squared minus 6x minus 3. And now I want you to list all the possible rational zero. Of fx. Okay, so now we can use the rational root theorem to do that. So I know that all the possible roots is come from p over q, where p is all the possible root from the coefficient, which means p could be 1 and 3. Of course, positive 1 and negative 1, positive 3 and negative 3. But since we have a positive negative, so we don't need to worry about that. And here, all the possible root of q is going to be 1 and 2, right? Those are the factors of 2. So that means all the possible root is going to be p over q. So 1 over 1, 1 over 2, or 3 over 1, 3 over 2, and positive and negative. So these are all the possible roots. They don't have to be the roots of the function, the polynomial, but all the possible root is going to be here. You can simplify it as positive and negative 1, positive and negative 1/2, positive and negative 3, positive and negative 3/2. Okay, so what will be the application to find in all of these possible roots? For example, let's use the same polynomial in here. So we have this polynomial. Now I ask you, hey, find me all of the horizontal intercept. How would you do that? Well, we know that the horizontal intercept is also the zeros or the roots of this function. If we have all of these possible roots, at least we know where to start with our synthetic function. For example, I can say, hey, let's use synthetic division, since I know that one of the root is 1 negative or positive 1 1/2, positive and 3, and positive and negative 3/2. We can start them with here by using long division. I have 2, 4, negative 1, negative 6, and negative 3. Okay, so if let's try 3. Since 3 is the possible root, so I have 2 times 3, I got 6, 10 times 3, 13, positive 29, and then I have 87, and then I have 81. Okay, so this is, we know that is far off. This is not going to be the root because we have a remainder of 240. Okay, so that means we can try another root. At least that gives you where to start. That's the whole purpose of this rational root theorem. Let's try 1. Let's try negative 1. So I got 2 times negative 1, I have negative 2. 2 times negative 2, I have negative 2. So I have a negative 3. Negative 3 times I have positive 3, gives you negative 3. Another positive 3 and 0. So now I know that, hey, negative 1 is one of the roots. So that means my polynomial can be written as x plus 1 times, this is x to the third, because your degree dropped from x to the fourth. After divided by 1x, you will have x to the cube. Okay, after that, well, that gives you easier to find another root. We repeat the same process in here, what we did, and then we keep factoring out till we get to a quadratic function, and then we can use the quadratic formula to find the rest of it. Okay, so here is the application of the rational root theorem. Let me know if you have other questions.